Now dear student, we are going to solve this question, and this question is question number 1.18. In this question it is given a point charge plus 10 microcoulomb is a distance 5 cm directly above center of a square of side 10 cm as shown in a figure. Fine. What is magnitude of electric flux through a square? Clear? So now concentrate on this screen. Let's suppose I am again drawing. Let's suppose here we have this is square. Clear? This square is perpendicular to this screen. Clear? And now side is given to you 10 cm, and let's suppose we place a charge at 5 cm distance above this plane. Clear? Our objective here in this question is to calculate flux. This is passing through this surface. Clear? Now actually you can see we can also draw this surface like this. Listen carefully. Yes or no? Now we can say this becomes a cube, and we placed here charge at this point. This is at the center of this cube. Yes or no? So we can write like this: net flux, this should be equal to 6 times of flux. This is passing through this square plane, and this is equal to net charge divided by epsilon naught. Yes or no? This is Gauss law. Yes or no? According to Gauss law, net flux, this is passing through a closed surface, it should be equal to 1 by epsilon naught times q net. Yes or no? So from here we can say phi s, this should be equal to q by 6 epsilon naught. Clear? So value of charge is given to us. This is 10 microcoulomb. So 10 into 10 to the power minus 6 divided by 6 multiply epsilon naught. Clear? Epsilon naught value we actually know very well. So we can write like this: 10 to the power minus 5 divide 6 epsilon naught. Clear? So how can we write like this? Phi net, or we can say value of phi s, this should be equal to 10 to the power minus 5 divided by 6 into 8.85 into 10 to the power minus 12. Clear? When this goes to the numerator, it becomes 10 to the power 7 divide 8.85 into 6. Clear? So if you multiply, we can write like this: 10 to the power 7, we have 30, we have 3, this is 51, we have 5, so this is 53. Clear? So we can say, we can write like this: 100 into 10 to the power 5, this is 53.1. Yes or no? So if you calculate, approximately you will find 1.8 into 10 to the power 5, and this is Newton per coulomb meter square. Clear? So this is value of, we can see, flux. This is passing through this plane surface. Clear to everyone? So this is all about this question. Now we are going to start question number 1.19. In this question it is given a point charge of 2 microcoulomb is at center of a cube Gaussian surface 9 cm on edge. What is net electric flux that is passing through this surface? Clear? So in this question it is given to us. Let's suppose here we have a cube. Let's suppose this is a cube. Clear? So this is cube. Let's suppose we place a charge q, that is between the center, or we can at the center of a cube. Now side is also given to you. Value of q, this is given to you 2 microcoulomb. Our objective here in this question is to calculate net flux. So phi net, according to Gauss law, we can write like this: this is 1 by epsilon naught times of q net. Clear? So we can say q net, value of q, this is given 2 into 10 to the power minus 6. Clear? Value of epsilon naught, we know 8.85 into 10 to the power minus 12. Clear? From here we can say this is 2 into 10 to the power 6 divided by 8.85. Clear? So we can write like this: 10 to the power 6 divided by, we can say this is 4.4. Clear? So approximately we can say, if we write like this, 10 divided by 4.4 into 10 to the power 5. 10 by 4 we have 2.5, so slightly less than 2. So we can say this is 2.1 into 10 to the power 5. Clear? So this is value of net flux passing through this cubical surface. Yes or no? And unit we have Newton per coulomb meter square. Clear to you? So this is all about this question. Now we are going to discuss question number 1.20. In this question it is given a point charge causes an electric flux of minus 1.0 into 10 to the power 3 Newton meter square per coulomb to pass through a spherical Gaussian surface of 10 centimeter radius centered on a charge. Okay, fine. Our objective here, if the radius of the Gaussian surface were doubled, then how much flux would pass through surface? Clear? So now concentrate on a screen. A point charge causes a flux. So value of finite, this is given. This is negative of 1.0 into 10 to the power minus 3 Newton meter square per coulomb. Clear? Now spherical Gaussian surface and radius is given to you 10 centimeter. Okay, fine. If radius of Gaussian surface were doubled, so let's suppose we are having point charge, and let's suppose this is Gaussian surface we are assuming. Let's suppose this is Gaussian surface. Clear? At this time we are having radius r. Now in this question it is given to you value of r doubled, then how much flux would pass through surface? It means, now what is situation? Listen carefully, I am again drawing this diagram. So let's suppose I am taking, this is a point charge q. Let's suppose initially we are having Gaussian surface like this, having radius r. Now let's suppose radius double. So when radius double, let's suppose it becomes like this. Yes or no? And let's suppose this is twice of r. Clear? Our objective in this question is to find how much flux would pass through surface when its radius doubled. Clear? So actually we know value of phi, this is given by E dot A. Clear? So if we take any cross section, we can say E and A both are in the same direction, because this is a negative charge, so we can say electric field lines is going in this direction. Yes or no? Or we can say area vector is outward direction. Clear? So we will find same situation at each point. Clear? So we can say here we are getting negative phi equal to minus A. Clear? But important part we have, we can write like this, kq divided by r square, and we can also write like this, this is 4 pi r square, because cross section area we are having 4 pi r square. Yes or no? But this is at position, we can say when we are talking about Gaussian surface 1. When we are talking about Gaussian surface number 2, what will happen? We can write like this. Now let's suppose phi dash. Clear? We can say minus kq divided by twice r whole square multiply, we can say 4 pi twice r whole square. Clear? So we can say twice r square cancelled out. It means we can say we are getting phi dash, this should be equal to phi. A very important conclusion we are getting here. Whenever we are changing radius of a Gaussian surface, but q net that is inside this surface, inside this Gaussian surface is same, we can say net flux that is coming outward or inward, it always remains same. Yes or no? It does not depends on a radius of Gaussian surface. Clear to everyone? So what is answer of option number A, part number A? How much flux would pass through the surface? Same flux which will pass through this surface. Clear? So our answer will be, this is equal to minus 10 to the power 3 Newton meter square per coulomb. Clear to you? Yes or no? Now if we talk about B part, what is value of point charge? So we can write like this, q by epsilon naught, this should be equal to we can say 10 to the power 3 Newton 10 to the power 3, because this is value of flux. Clear? Here we are taking minus because it is given in a question. So we can write like this, q, this should be equal to minus 10 to the power 3 8.85 into 10 to the power minus 12. Clear? So from here we can write like this, minus 8.85 into 10 to the power minus 9 coulomb. Clear? Or you can write like this, minus 8.85, this is nanocoulomb. Clear to you? Definitely we will get here negative charge, because for the negative charge, electric field lines always come inward direction. Yes or no? And flux is given to you negative, it means this is inward flux. Yes or no? So value of Q we are getting minus 8.85 nano coulomb. Clear to everyone? Now we are going to discuss question number 1.21. In this question it is given a conducting sphere of radius 10 centimeter has an unknown charge. Okay. If the electric field 20 centimeter away from center of sphere is 1.5 into 10 to the power 3 Newton per Coulomb and point radially inward, very important. What is net charge on sphere? Clear? So now concentrate. It is given a conducting sphere. A conducting sphere means what? We can say all charge is situated on the surface of a sphere. Clear? So now we can say like this. Let's suppose here we are having this is a conducting sphere. Clear? And let's suppose this is center of this sphere. So radius is given, this value r, that is 10 centimeter. Clear? Conducting sphere we have, so let's suppose we can say all charge this is present at the surface, this one. Clear? So this is value of charge Q we have. Okay. Now electric field 20 centimeter from the center. So let's suppose if we are talking about at any point P, let's suppose this is point number P. Clear? And distance is given 20 centimeter, this is P. Clear? So value of electric field at point P, this is given by KQ upon R square. So this is only magnitude. Clear? But it is also given, it points radially inward. Clear? So direction of electric field is given to you in this direction. Clear? So definitely we can say here we are not having positive charges, here we are having negative charges. Yes or no? Yes or no? So we can say actually if we draw sphere like this. Clear? Let's suppose this is center. Clear? And radius is given to you 10 centimeter. Clear? And here we are having negative charge that is present on this sphere. Yes or no? Clear? So directly you can say you have to calculate value Q in an you have to calculate first magnitude of Q and your answer should be with minus sign. Clear? So how can we calculate value of electric field is given to you 1.5 into 10 to the power 3 Newton per Coulomb. Clear? So we can write like this, value of K we have 9 into 10 to the power 9 into Q, don't know, this is our objective. Value of R, so value of R we have 20 centimeter, so 20 into 10 to the power minus 2 whole square, this should be equal to, we can write like this, 3 by 2 into 10 to the power 3. Clear? From here we can say this is 9 into 10 to the power 9 into Q divide by, we can say this is 2 into 10 to the power minus 1, so 4 into 10 to the power minus 2. Clear? And this should be equal to 3 by 2 into 10 to the power 3. We can say this is 10 to the power 6. Yes or no? We can say this is 3. This one we have 2. Clear? So how can we write value of Q? So we can say this is equal to 3 Q into 10 to the power 6 divide, we can say 2 into 10 to the power minus 2, this should be equal to 1. Clear? So value of Q 3Q into 10 to the power 8, this should be equal to 2. Clear? So we can write like this, Q 2 by 3 into 10 to the power 8. Clear? So from here we can write like this, 20 by 3 into 10 to the power minus 8, so this is minus, we can say, we can write like this, 20 by 3 into 10 to the power minus 9 Coulomb. Yes or no? So from here we can say this is 6.67 into 10 to the power minus 9 Coulomb. Clear? So we can say value of Q, this is given by value of Q, this is equal to minus 6.67 nano Coulomb. Clear to you? So value of charge we have minus 6.67 nano Coulomb. Clear? So this is our answer. Clear? Now dear student, we are going to discuss question number 1.22. A uniformly charged conducting sphere of 2.4 meter diameter has a surface charge density of 80 microcoulomb per meter square. Number A, find charge on a sphere. Second, what is total electric flux leaving surface of the sphere. Clear? So now listen carefully. Parameters, this is given to us, diameter of a sphere 1.24 meter, clear, or that is 2.4 meter, clear. So what is radius of a sphere? We can write like this, radius, this is given by d by 2 and this is 1.2 meter, clear. Surface charge density is given to you 80 into 10 to the power minus 6, this is coulomb per meter square, clear. Okay, so we can write like this. Number A part, our objective in this question is to calculate total charge on a sphere. So we can say sigma, this is equal to charge per unit area. Always remember, surface charge density means charge per unit surface area. So how can we calculate charge? This is sigma and 4 pi, this is r square, clear. So now if we put all the values, we can write like this, sigma, this is equal to Q, this is equal to sigma. Value of sigma we have 80 into 10 to the power minus 6, clear, multiplied with 4 pi and this is 1.2 whole square, clear. So dear student, if you solve it, you will find 1.45 into 10 to the power minus 3 coulomb. Yes or no? So this is value of charge that is present on the surface of a sphere. Yes or no? Now we are going to solve option number option number B, clear. Question number B is given to you, what is total electric flux leaving surface of a sphere, clear. So we can say total flux, this is given by Q net upon epsilon naught according to Gauss law, clear. Q net is given to you 1.45 into 10 to the power minus 3 divided by 8.85 into 10 to the power minus 12 we have. Yes or no? So if you calculate, you will find here value 1.6 into approximate, you will get 10 to the power 8 Newton, clear. We can say Newton per coulomb into meter square, clear. You can easily calculate. You can also calculate like this, 1.45 divide 8.85 into 10 to the power 9, clear. Now we can say almost, we can say here we are having 5 times or 6 times, almost 1 by 6. So we can say 0.16 we will find, and this is multiplied 10 to the power 9. So we will get 1.6 into 10 to the power 8, this is Newton meter square per coulomb, clear. So this is answer of this question, clear. Now dear student, we are going to solve question number 1.23, and in this question it is given to you, we have an infinite line charge and it produces an electric field of 9 into 10 to the power 4 Newton per coulomb, clear, at a distance of 2 centimeter. So we have to calculate linear charge density, clear. So I think you should know this about this formula. This is very popular formula. Let's suppose here we are having linear charge. Let's suppose I am taking here, this is positive charge, clear, and let's suppose this is going to infinity, this is also going up to infinity, clear. So let's suppose this distance we have, that is r, clear. And let's suppose we want to know what is electric field at point P due to this line charge. We can say it is given by EP, this is equal to 2k lambda upon r, clear. Sometimes people also write, student also write this formula like the 2 pi epsilon naught into earth, we have same formula, clear. So we can write like this. Actually what is our objective in this question is to calculate linear charge density, means charge per unit length, yes or no. So electric field value is given to you, so we can write like this, 9 into 10 to the power 4, it should be equal to 2, value of k, we have 9 into 10 to the power 9 and multiplied with lambda divided by r. Value of r we have, this is 2 centimeter, so 2 into 10 to the power minus 2, clear. So from here we can say 2 and 2 is cancelled out, so 9 and 9, this is also cancelled out, clear. We can say this one is also cancelled out, 10 to the power 5, so 10 to the power 5 multiplied, we can say lambda, this should be equal to 10 to the power minus 2, clear. So from here we can say lambda, this is given by 10 to the power minus 7, this is coulomb per meter, clear. We can also write like this, this is 10 to the power minus 1 micro coulomb per meter, yes or no. So we can say this is equal to 0.1 micro coulomb per meter, clear. So this is value of linear charge density in this question, clear to you. So this is all about this question. Now dear student, we are going to solve question number 1.24. Two large thin metal plates are parallel and close to each other. On their inner faces, the plates have surface charge density of opposite signs of magnitude 17 into 10 to the power minus 22 coulomb per meter square. Clear? What is value of electric field in the outer region of first plate, in the outer region of second plate and between the plates? Clear? So now concentrate on a screen. In this question it is given to you. Let's suppose here we have two plates and let's suppose these are the two large plates. Clear? And it is also given both the plates are having some charges. So let's suppose I am assuming this is having positive charge and let's suppose this is negative charge plate. Yes or no? Let's suppose this is plate number 1 and this is plate number 2. Now let's suppose if we want to calculate value of electric field, that is in the region, outer region of first plate. So let's suppose if we want to calculate at point P. Clear? So direction of electric field due to 1, we can say in this direction, that is E1. Listen carefully. Clear? And direction of E2, we can say in the opposite direction E2. Now you know, due to a large plate, we have value of E1 equal to E2 and this should be equal to sigma upon 2 epsilon naught. Clear to everyone? Yes or no? Yes. So this is sigma upon 2 epsilon naught. Clear? Now if we find value, let's suppose here at point Q, we can say E2 now in this direction and E1 is in this direction and magnitude is same because it does not depends on the distance from a plate. Yes or no? So from here we can say if we find E net at point, we can say Q or P. So we can say this should be equal to 0. Yes or no? Because both are having same magnitude but direction is opposite. So with this is, we can say Newton per Coulomb, this is 0. So for option number, for part number A and part number B, we have answered this is 0 Newton per Coulomb. Clear to you? Yes or no? Yes. Now our next objective here is to calculate value of electric field between the plates. Yes or no? So now concentrate. Now listen carefully. Let's suppose I am assuming here at point R. Now due to plate number 1, we can say electric field in this direction, this is E1, and we can say due to 2, electric field in this direction, that is E2. Clear? So we can write like this, E net, this should be equal to E1 plus E2. Clear? So now we can say this is sigma upon 2 epsilon naught plus sigma upon 2 epsilon naught. Clear to you? So this is equal to sigma upon, we can say epsilon naught. Clear? Our objective here in this question is to calculate value of E. Clear? So now we can say sigma, this is given to you 17 into 10 to the power minus 22. So 17 into 10 to the power minus 22 divided by epsilon naught. Epsilon naught we have 8.85 into 10 to the power minus 12. Yes or no? So if we calculate, we can say this is 10 to the power minus 10. This is approximate, we can say 9. Clear? Or we can say 9 almost equal to, we can say 18. So this is 1 point, let's suppose we are taking 1.8. Clear? So 1.8 into 10 to the power minus 10, or you can say approximate, this is 9. 1.9 into 10 to the power minus 9, and value we have, this is Newton per Coulomb. Clear? So this is value of electric field between these two parallel plates. Clear to everyone? So this is solution. Now dear student, we are going to solve this question, and this question is related to Millikan oil drop experiment. Actually in this question we have an oil drop and we are providing some charge on that oil drop. Now if we place that oil drop in an electric field, definitely we can say an electric field, due to electric field electric force will act on that oil drop. Clear? And we know that is equal to F equal to QE. Yes or no? So let's suppose that oil drop is in equilibrium. At that time we will find QE, it should be equal to mg. Yes or no? So QE should be equal to mg. Yes. So from there we will find in this question the radius of this drop. Clear? So now we are going to solve this question. Concentrate on a screen. Now listen carefully. Let's suppose here we have an oil drop. Let's suppose this is an oil drop. Clear? Let's suppose mass of an oil drop we have m. So we can say here mg force is acting on this oil drop. Now let's suppose according to question it is given we are providing 12 excess electrons. 12 excess electrons means we can say here we have negative charge on this oil drop. Yes or no? So now we are saying let's suppose electric field in this direction, because this is a negative charge oil drop. So we can say force this is act on the opposite direction of an electric field, and this is equal to QE. Now let's suppose if we talk about equilibrium position, it means now this drop is in equilibrium, it means we can say mg, it should be equal to QE. Clear? So from here we can write like this, mg this should be equal to QE. Clear? Now we can say because density is given to you, so we can write like this is density volume multiply G. Clear? And Q. Because here it is given we have 12 excess electrons, so we can write like this is n times of E. Yes or no? And this is multiplied with E. Now actually they are asking to you radius of oil drop. It means we can assume that any oil drop is having a spherical in shape. So how can we write volume? Volume is given by 4 by 3 pi r cube multiply G. This should be equal to NE multiply E. Clear? So from here we can write like this, r cube this should be equal to 3 NEEE divided by, clear? We can write like this 4 pi rho and this is G. Clear? So r cube this is equal to 3 NEE divided by 4 pi rho multiply G. Clear? So from here we can write like this, r this is given by 3 NEE divided by 4 pi rho and this is G power 1 by 3. Clear? Now we will put all the values that is given in this question. Yes? So now concentrate. Now we can say first we can write like this 3. Clear? Excess electron we have 12 multiply charge of an electron 1.6 into 10 to the power minus 19 multiply value of an electric field, this is given to you 2.55 into 10 to the power 4 and divided by, clear? Here it is given this is 4 into 3.14 multiply rho into G. Density is given to you in gram per centimeter cube. First we convert in kilogram per meter cube. So we can write like this 1.26 into 10 to the power 3 kilogram per meter cube. Clear? And last we have value of G, this is 9.81. Clear? And power is given to you 1 by 3. Clear to everyone? Yes or no? So now if you write all the if you calculate here, you can calculate like this 3 into 12, we can say this is 36 into 1.6 into 2.55 into 10 to the power minus 15. Clear? Divided by, clear? It is given 4 into 3.14 into we can say 1.26 into 9.81 into, or we can say 10 to the power 3 we have, so we can write here 10 to the power minus 18. Clear? And this power 1 by 3. Clear? So if you calculate here, you can take here approximate calculation, and finally what you will get here, that is important. Here you will get 9.81 into 10 to the power this is minus 4 mm. Clear? You can easily calculate this is 10 to the power minus 18 power 1 by 3, it means 10 to the power minus 6. Clear? Here we have approx 3 or we can say approx 2.5. So you can write this is 5 by 2. Clear? And approximate this is you can write 5 by 4. Clear? This is pi, it means 22 by 7. So if you write all these things, you will get here approximate result this one. Clear? So radius of this oil is given by 9.81 into 10 to the power minus 4 mm. Clear to everyone? So this is all about this question. Now dear student, we are going to solve question number 1.26. In this question it is given which among the following curve that is shown to you here cannot possibly represent electrostatic field line. So if you want to solve this type of question, you should know about some properties of electric field lines. Clear? Like electric field lines are the imaginary curve at any point. If we draw the tangent, it represents direction of an electric field, number 1. Second, electric field lines never forms a closed loop. Second, electric field lines never intersect to each other. Electric field lines always start from positive charge and it always ends to a negative charge. Yes or no? So you can actually, if you know all about this property, you can easily solve this question. Clear? Now you can say concentrate. If we concentrate on figure number A, we can see the electric field lines that is showing here, that is in outward direction. Clear? And positive charge that is provided to this conductor, we know the charge is distributed on a surface. Fine. But this type of electric field lines is possible or not? I will say no. Option number A, or we can say figure number A, is wrong. Why? Because whenever electric field lines that is passes through or incident on a conductor, it always incident perpendicular to the surface. Why? Because we can say here we have an equipotential surface. Yes or no? You should always keep in mind electric field lines always incident on a conductor perpendicular to its surface. So we can say this figure is not possible. Clear? Now if we say that we can say B number, this may be the representation of electric field lines. No. Why? Because we know electric field lines always start from positive charge and ended to a negative charge. Clear? So this one is wrong. Clear? You can also see from this diagram, we are actually observing the electric field lines is coming out from negative charge and it is ended to positive charge. So we can say this is also a wrong figure. Yes or no? Now if we concentrate on figure number C, now we can say yes, from positive charge electric field lines is going in an outward direction, and here also we have positive charge electric field lines is going in outward direction, and between these two positive charge, definitely if we calculate by some formula, we always find electric field value 0. So we can say they will actually repel between at this region. Yes or no? And we can say this is a perfect diagram of two charges having same polarity, or that is the positive charge. Clear? So we can say yes, this is the diagram. It can be represented between when we have two positive charge. Clear? Yes or no? So whenever we have two positive charge, we can draw electric field lines like this, and let's suppose we are having negative charge. So the arrow diagram, it will be like this if we have negative charge. Clear to you? Yes or no? Yes. So this is the correct figure. If we concentrate on figure number D, directly we can say this is wrong. Why? Because you can observe here electric field lines are intersecting to each other. So whenever electric field lines intersect to each other, at intersecting point we have two direction of an electric field, and that is not possible. Clear? So figure number D is also wrong. If we concentrate on figure number E, we can see here inside it is actually forming a closed loop, and electric field lines never form a closed loop. Clear? But magnetic field lines, magnetic field lines definitely form a closed loop. Yes. So you will actually understand in a chapter number 5, the magnetic field lines always start from a north pole and it is ended to a south pole, that is outside the magnet, but inside the magnet it will move from south pole to north pole. So it may form a closed loop, but electric field lines never form closed loop. Yes. So we can say E figure is also wrong. Clear? So which figure can represent electrostatic field lines? Only option number C. Clear to everyone? Now we are going to solve question number 1.27, and in this question it is given to you, and actually my dear student, this is very important question, because till now whatever the question we have solved, it is having electric field that is constant, it is not varying with space. Clear? But in this question we can say electric field is actually varying in a z direction. Clear? So now concentrate. In a certain region of space, electric field lines is along z direction throughout. Clear? So we can see, according to question, we can see electric field lines in z direction. Clear? So we can say this is electric field direction. Let's suppose I am assuming here this is positive x. Clear? This is positive y, and let's suppose this is positive z direction. Clear to you? Okay. So electric field in positive z direction, the magnitude of electric field is however not constant but increases uniformly along positive z direction. It means we can say electric field is increasing in this direction. This is given to you. Okay. At the rate of 10 to the power 5 Newton per coulomb per meter. It means here it is given dE by dz. Clear? It is given to you 10 to the power 5 Newton per coulomb and per meter. This is given to you. Okay, fine. What are the force and the torque experienced by a system having a total dipole moment in negative z direction? So if we are talking about dipole moment, so dipole moment means we can say in negative z direction, the direction of an electric dipole moment is given by minus q to plus q charge. It means we can observe here minus q charge we have here, and we can say this is plus q charge. Yes or no? Clear to you? And it is also given what are the force we have to calculate and torque we have to calculate. Okay, fine. Electric dipole moment, this is given 10 to the power minus 7 coulomb per meter. So we can say this is given by 10 to the power minus 7 coulomb meter. Clear? So now listen carefully. Whenever we place an electric dipole that is having a distance 2a between them in an electric field, and important part we have, this electric field is not varying with electric field is actually varying with space. This is given to you because 10 to the power 5 Newton per coulomb per meter is given to you. Yes. So if we talk about electric field, so on this charge force is acting in this direction, this is F1, and on this we can say this is F2. Clear? How can we write value of F1? F1 we can say this is equal to Q into E1. Clear? And F2 we can say this is Q into E2. Direction we have already seen logically. Clear? So value of Q we have Q, and let's suppose we are assuming, I am assuming electric field is here 1 Newton per coulomb. I am assuming, actually it is not given in a question, I am assuming E1 equal to 1 Newton per coulomb. Now you can say how can you assume, because we will find here difference, because our objective in this question is to calculate net force on this dipole. So definitely this one will be cancelled out. Clear? So how what is value of E2? Listen carefully. At this position we have electric field, this is 1 Newton per coulomb, and in this question it is given it increases at the rate of 10 to the power 5 Newton per coulomb. Yes or no? And per meter. So we can say here we are having distance, this is 2a, so we can say 2a multiply 10 to the power 5. Yes or no? Clear? Here we have electric field, let's suppose 1. Here it is increases 10 to the power 5 Newton per coulomb per meter. So we have total distance 2a, so it is increases by, we can say total electric field at position 2. We have this is 1 plus 2a into 10 to the power 5. Clear? This is position number 1 and position number 2. Clear? Now if you find here net force we can say this is Q of delta E. Clear? Or you can also write like this, this is equal to Q E2 minus Q E1. Yes or no? So we can say this is equal to Q E2. Value of E2 we have 1 plus this is 2a into 10 to the power 5 minus 1. Yes or no? Clear? So we can say 1 and 1 is cancelled out. Clear to you? So from here we can write like this, F net, this should be equal to Q into 2a into 10 to the power 5. Clear? Okay, Q into 2a. Q into 2a means what? Q into 2a. This is what? Electric dipole moment? Yes. So we can say F net, this is given by P into 10 to the power 5. Clear? So from here we can write, how can we calculate net force? Value of F net, it is given by P into 10 to the power 5. P value is given 10 to the power minus 7. So 10 to the power minus 7 into 10 to the power 5. So from here we can say this is 10 to the power minus 2 Newton. Clear to everyone? Yes or no? So we have value of force 10 to the power minus 2 Newton. But what about torque? Now you can see actually both forces are acting along the same line. So we can say it will not form, it will actually not rotate this dipole. Yes or no? So final answer I can say net force we have 10 to the power minus 2 Newton. Clear? And direction definitely minus q to plus q. Clear? Because this force is more compared to this one. And net torque we can say this is 0. Clear? So this is all about this question. Clear? Now dear student, we are going to discuss question number 1.28, and in this question we have 3 parts A, B and C. Clear? In the first part it is given to you a conductor capital A, as you are seeing in the screen. A conductor capital A with cavity as shown in a figure is given a charge capital Q. Fine. Show that the entire charge must appear on the outer surface of a conductor. Clear? So first situation is given to you like this. Let's suppose we have a conductor and we have a cavity inside this conductor, and now we are providing total charge Q on this conductor. Clear? Now we have to actually prove here that the entire charge is appearing on its surface. Clear? So now concentrate on a screen. Let's suppose actually I am drawing here a Gaussian surface. So let's suppose I am drawing here a Gaussian surface. This is very close to this cavity. Clear to you? Let's suppose this is Gaussian surface and it is very close to cavity. Now we know, we can see, if we talk about Gauss law, according to Gauss law we can see finite this should be equal to Q by epsilon naught. Yes or no? And we also know this is also equal to integration of E dot dA. Clear? Now we know inside a conductor we have electric field, this is 0. Clear? So when in the we can say in a cavity we have E equal to 0. Clear? So when E equal to 0 we have, from here you can say Q, this should be equal to 0. Now listen carefully, this Q is what? This Q is the net charge, this is present inside this cavity, it should be 0. Clear? Now you can see in this cavity at this time we do not have any charge. Clear? So we can say here we will not find any charge. So what will happen when we are providing charge Q? Then this charge will be distributed all over its surface. Clear? So like this we can prove here that if we are providing charge Q, and let's suppose this is positive charge. So when we are providing charge Q on a conductor, this total charge will actually distributed on its surface and there is no charge, this is present inside. Clear to everyone? So I think part number A is clear to you. Yes or no? Clear? Now let's suppose situation is changes. In the situation number B, it is given to you another conductor B with charge Q is inserted inside a cavity. Means now what we are doing, we are placing here a conductor, and let's suppose we are providing here a charge Q. Yes or no? And important part, we have this A conductor and the B conductor are isolated from each other. Yes or no? So now we have to find that actually we have to prove the total charge on the outside surface is capital Q plus small q. Clear? So now what we do? Again actually we will draw here first Gaussian surface. Clear? So concentrate. Let's suppose I am drawing this figure here again. Let's suppose this is a diagram. Let's suppose here we have a conductor, and let's suppose this is conductor inside which we have a cavity, and this is E. Let's suppose now we are placing a small charge Q. Let's suppose this is charge Q, and let's suppose B. A is B isolated. Clear? Now what I am doing? I am drawing here a Gaussian surface. So let's suppose I am drawing here a Gaussian surface. This is very near to this cavity. Clear? Let's suppose this is Gaussian surface. Now I can say definitely, because inside this Gaussian surface we have a charge, so definitely we will find here net electric field. Clear? So we can write like this: phi net, this should be equal to Q by epsilon naught. This should be equal to integral of E dot dA. Yes or no? Now our objective here is to find that what is total charge that is present on the outer surface of conductor A. Clear? So actually we are providing total charge Q to this conductor A. Clear? But we know, if we talk about this Gaussian surface, inside which we can say we have a cavity. So in the cavity we can see there should be net electric field is to be 0. Yes or no? Whenever we find cavity inside a conductor, net electric field is 0. Clear? So actually we have already charge Q is present. It means if we want that electric field should be 0, at that time we have to introduce a charge minus Q here, so that the net charge inside the cavity becomes 0. Yes or no? It means we can say, let's suppose if I provided minus Q charge on the inside surface of conductor A, then we can say net charge, this is inside this Gaussian surface, is 0. Yes or no? But we know if we are introducing minus Q, definitely we have to add here plus Q, so that the total charge on conductor A, it remains capital Q. Yes or no? So now we can see like this we can prove the total charge on this is present on the outer surface of conductor A. This is capital Q plus Q when we place a conductor, or we can say when we place a charge small q inside a cavity. Clear to everyone? Yes or no? So this is all about part number B. Clear? Now we have part number C also. A sensitive instrument is to be shielded from strong electrostatic field in its environment. Suggest a possible way. So let's suppose we have a sensitive instrument and we want to prevent it. So what we can do? We can place that instrument within a hollow cavity. Yes or no? So let's suppose we have a conductor and inside that conductor we have a cavity. Clear? So if we place that instrument in that cavity, we know electric field in a cavity becomes 0. Yes or no? When electric field is 0, it means we can say now there will be no damage by external electric field on that instrument. Yes or no? So like this we can prevent any instrument from electrostatic field in environment. Clear to everyone? So this is all about this question. Now dear student, we are going to discuss question number 1.29, and in this question it is given a hollow charge conductor has a tiny hole cut on its surface. Okay, fine. Show that electric field in that hole is sigma upon 2 epsilon naught n cap, where n cap is unit vector in the outward normal direction and sigma is surface charge density near hole. Yes or no? So now concentrate on a screen. Let's suppose I am taking here an example of a sphere. Clear? We can take any example of a conductor. So let's suppose we have this hollow sphere. Let's suppose like this. Clear? And let's suppose if I am talking about an outermost point, let's suppose this is a point P. Clear? And let's suppose actually I cut a small part on its surface. Clear? So let's suppose this tiny hole is cut on its surface. Clear? It means this part is removed. Clear to everyone? So now if we talk about total electric field at point P by all the we can, if we are assuming complete sphere, so total electric field at point P, this is given by, let's suppose I am assuming this as 1 and let's suppose this sphere I am assuming this is 2. Clear? This one is 2. Clear? So let's suppose if I provided here a charge that is plus q. Clear? So we can say electric field due to 2, we can say in this direction this is E2, and due to 1 we can say this is E1. Clear? Now we know if we have a charge conductor, electric field outside at any point, this is given by E equal to KQ upon R square. Clear? R is the distance of that point from a center. Clear? So we can also write like this, 1 upon 4 pi epsilon naught into charge Q. We can say, we can write in terms of surface charge density sigma into surface area, we have 4 pi r square and it is divided by r square. So r square and r square, this is cancelled out, 4 pi and 4 pi cancelled out. So from here we can say E, this should be equal to sigma upon epsilon naught. So my dear student, this E is what? This is E net. Clear? And this E net actually consists of two electric field E1 and E2, and both are in same direction. So we can write like this, E1 plus E2, this should be equal to sigma upon epsilon naught. And most important, let's suppose we are assuming unit vector in the outward direction, that is n cap. So we can write like this, this is n cap and this is net electric field. Yes or no? So this is value of net electric field that is outside. Clear? And let's suppose this is equation number 1. Clear? You can write like this. Yes or no? Now if we consider at any point, let's suppose I am considering here point number Q. Clear? Now we know inside a conductor we always find net electric field 0. Yes or no? So we can say, let's suppose this is E1 and let's suppose this is E2. So we can say here E1 and E2 definitely will be in the opposite direction, so that we will find net electric field, this should be 0. So this is equal to E1 minus E2 and it should be equal to 0. Clear? So from here we can write like this, E1 this should be equal to E2. Clear? So now if we utilize this relation in this equation, how can we write? So we can write like this. Actually here we are just writing magnitude because direction is opposite, so E1 equal to E2. Clear? So if we talk about magnitude, we can say E1 plus E2, this should be equal to sigma upon epsilon naught. Clear? And direction is along the vector, that is outward, normal outward direction. This is nk. Clear? So we can write like this: 2 times of E1, this should be equal to sigma upon epsilon naught, and we can say E1, this is given by sigma upon 2 epsilon naught, and most important, if we write in a vector form, this should be nk. Yes or no? So value of E1, this is given by sigma upon 2 epsilon naught and nk. Clear? So this is answer, and this is the proof of this question. Clear to you? Yes or no? So now dear student, we are going to discuss question number 1.30, and we have a here question: obtain the formula for electric field due to a long thin wire of uniform linear charge density A without using Gauss law. Clear? So actually uniform charge density is given to us, that is lambda. Clear? And without using Gauss law, we have to prove value of electric field. Clear? So now concentrate on a screen. So let's suppose I am assuming, let's suppose we have infinite long wire, and let's suppose we provided a charge q. Let's suppose we provided charge q. Clear? And this is going up to plus infinity this side, and this is minus of infinity. Clear? Yes. Now let's suppose we are taking here one point. Let's suppose this is point P, where we want to find value of electric field. Clear? So we have here point P, and at this point we will find value of electric field. Clear? So now let's suppose this point P is situated at a distance y from this wire. Clear? Now let's suppose we are taking here a very small element, and let's suppose this element is situated at a distance x from this intersecting point, from this point. Clear? And let's suppose thickness is here, this is dx. Clear? And let's suppose charge, this is present on this small element, this is dq, and it is written, that is lambda times of dx. Yes or no? It can be written like this: dq, this should be lambda times of dx, because linear charge density is defined as charge per unit length. Clear? So we can write like this. Yes or no? Now if we join this point from this element, let's suppose I am assuming this distance is r. Clear? So now we can see, if we draw here direction of electric field, it will away from this point P, and let's suppose this is D. Clear? So now we can say here we will find two components. Clear? Number one component in this vertical direction and another component in horizontal direction. Clear? We can say this is what? DEY, and this is DEX. Clear? So DEY and DEX we have. Clear? Now let's suppose I am assuming this angle is theta, so this angle is also theta. Clear? So first I will find value of electric field due to this small element, so I can write like this: dE, this is given by K dq upon r square. Clear? So we can write like this: K dq, this is lambda times of dx upon r square. We can say this is x square plus y square. Clear? If we consider this right angle triangle, we can say this is x square plus y square. Clear? Now we can see, actually we have taken a small element on the right side. So if we take same element on this left side, and if we join this element from here to here like this, so if you see net electric field, this will in this direction. Clear? Again we will take two component, one in horizontal direction, another one is vertical direction. So in a horizontal direction we can say the net electric field, it will be cancelled out, or we can say electric field is cancelled out. Why? Because magnitude is same. You can calculate, magnitude is same but direction is opposite. So if we find net electric field, we will always find in y direction. So we can write like this: DEY. Clear? If we are taking component of D in this direction, we can say this is equal to integral of dE cos of theta. What about limit? Because this is a very long wire, so we are taking limit from minus infinity to plus infinity. So minus infinity to plus infinity. Clear? Now I am going to write value of dE. Clear? So we can write like this: E net, this should be equal to minus infinity to plus infinity. Clear? value of d, we can say this is k dq divided by, we can write like this, x square plus y square. Clear? And we have here cos of theta also. Clear? Now listen carefully. Actually we can also write like this, value of tan theta. From this triangle we can say tan theta is given by x by y. So x, this should be equal to y tan of theta. Clear? If you differentiate this x with respect to theta, we can write like this, y sec square theta d theta. Clear? Now we will put this value here. Clear? So now first I am writing k, this is outside. Clear? dq, we can write like the dq equal to lambda times of dx. Clear? From minus infinity to plus infinity, this is dx upon. Clear? Now I am writing here value of, or first I am writing like this, x square plus y square, and this is cos of theta. Clear? Now we will put value of x in this equation. Clear? And value of dx also. Clear? So we can write like this, k 1 upon 4 pi epsilon naught multiply lambda. We can also write like this, because this is minus infinity to plus infinity, so we can multiply it with 2 here, and we can write like this 0 to infinity. Clear? And value of dx, we have this is y sec square theta, this is d theta. Clear? And we have here cos of theta also, and divided by, this is x square plus y square. X value is given to you y tan theta, so we can write like this, y square, this is tan square theta plus y square. Clear to you? Yes or no? So now our just objective here is to solve this equation. Clear? Now actually we can see here, we have converted this expression in terms of theta, but now we will change here limits also, because these are the limits for x. Clear? So if we put value of x here, so we will find value of tan theta, this is 0, and if we put value of x pi by 2, then value of theta we will find if we put value of x infinity, then we find theta, this is pi by 2. Yes or no? So now I am writing like this, this is lambda upon 2 pi epsilon naught. Clear? From 0 to pi by 2. Clear? Now listen, I can write in denominator like this, y square 1 plus tan square theta. Yes or no? And I can write like this, this is y sec square theta, this is d theta, and this is cos of theta. Clear? So now we can say in the denominator 1 plus tan square theta, this is sec square theta. So lambda upon 2 pi epsilon naught from 0 to pi by 2 y d theta, or you can write like this, 1 y and y is cancelled out, we are taking this y outside. Clear? So sec square theta d theta, this also become sec square theta. So sec square theta is cancelled out, so we can write like this, this is cos of theta d theta. Clear? So from here we can write like this, lambda upon 2 pi epsilon naught y, this is sin theta from 0 to pi by 2. Clear? So if we put here all the values, we can easily get value of net electric field. So net electric field, this is given by, we can write like this, lambda upon 2 pi epsilon naught y, and this is 1 minus 0, because sin pi by 2 minus sin 0, sin pi by 2 value we have 1. Clear? So from here we can say our correct answer, or our answer of net electric field, this is lambda upon 2 pi epsilon naught y, or we can write like this, this is 2k lambda divided by 2k lambda upon r, so we can write like this, this is 2k lambda upon y. Yes or no? So you can also get this expression from the Gauss law. Clear? You have to draw one Gaussian surface and you can easily get it, but in this question it is given, we have to find value of electric field without using Gauss law, so we can find that expression like this. Clear to everyone? So a very simplified method that I tell to you here. Yes or no? So this is all about this question. Clear? Now dear student, we are going to discuss question number 1.31, and in this question it is given to you, it is now stabilized that proton and neutron, which constitute nuclei of ordinary matter, are themselves built out of elementary elements, we can say that is quarks. Clear? A proton and neutron consist of their 3 quarks each, 2 types of quark, so called up quark and down quark, and the value of the charge, this is also given to you, plus 2 by 3 e for up quark and minus 1 by 3 for down quark. Okay, it together build up electron, and we can say it also build up ordinary matter. So suggest a possible quark composition for proton and neutron. Actually this is a concept. Actually we know a term, that is quantization of electric charge. Clear? Or we can say the charge that is present on a body, it should be multiple integral of a basic charge, that is charge of an electron. But after some time it is also seen that we can also divide charge of one electron in up quarks, down quarks, and so on. Yes or no? So in this question it is given, let's suppose we are actually breaking proton and neutron into up quarks and down quarks. We have to find here actually composition. Clear? So now listen carefully. We know charge of a proton, this is equal to E, and if we talk about charge of neutron, we can say charge of neutron, this is 0. Yes or no? Now it is also given, now proton and neutron, it is made up of quarks, and up quark and down quark. So it is given here in this question, charge of up quark, this is equal to plus 2 by 3 e. Clear? And it is also given charge of, this is down quark, so down quark, this is given minus 1 by 3 e. Yes or no? So let's suppose we are assuming in a proton we have x number of up quark and remaining we have down quark, and totally it constitutes a charge, that is charge of an electron. Yes or no? So let total up quark in proton, this is x. Clear? So what is down quark in proton? This is we can say total we have 3 quarks, so we can write like this is 3 minus x. Clear? But we know total charge on a proton, we have charge of an electron, so we can write like this. We have total number of up quark, this is x, and charge of one up quark we have 2 by 3, so multiply 2 by 3 e. This is total charge present on up quark. Then we can write like this, plus 3 minus x, we have total charge on down quark, this is minus 1 by 3 e. Clear? And it should be equal to charge of an electron. Yes or no? So we can say electron, this is cancelled out. So from here we can write like this, 2x by 3 minus 3x minus x divided by 3, and it should be equal to 1. Clear? From here you can write like this, 2x minus 3 plus x, this should be equal to 3. Yes or no? So from here we can write like this, 3x equal to 6, x equal to 2. It means we can say in a proton we have 2 up quarks, and how many we have down quarks? That is 1, because we have total number of quark 3. Yes or no? So we have 2 up quark, and if we calculate y, this is 3 minus 2, we can see 1. Clear? So for a proton, what is composition? What is a composition? I can say for a proton we can write like this, UUD. 2 up quark we have, and we have 1 down quark. Yes or no? Clear? So now if we calculate same for, I am writing here, for proton I am writing, for proton, this the composition we have UUD. Clear? Now we are going to calculate for neutron. Clear? So we know the charge on a neutron is 0. Clear? So we can write like this, total number of, let's suppose I am assuming total number of up quark in a neutron is y, so this is 3 minus y. Clear? Charge of an up quark, this is 2 by 3 e minus, or we can say plus 3 minus y, this is minus 1 by 3 e, and total charge we have 0. This is for neutron. Clear? So we can write like this, 2 by e by 3 minus e by 3, 3 minus y, this should be equal to 0. So we can take here common e by 3, this is 2y minus, we can say 3 minus y, and this should be equal to 0. Clear? Now we know E by 3 it cannot be 0. It means this bracket terms is equal to 0. Clear? So now we can write like this, 2y minus 3 plus 3y, this should be equal to 0. Yes or no? Clear? This one. Yes or no? Clear? So from here we can write like this, 3y, this should be equal to 3. So y equal to 1. So in a neutron we have one up quark, and how many we have down quark? So if we talk about down quark, this is 3 minus y, and we can say this is 3 minus 1, this is equal to 2. Clear? So if we write here composition of a neutron in terms of up quark and down quark, we can write like this, this is UDD. Yes or no? So we can say for a neutron we have total 2 down quark and 1 up quark. Clear? So for neutron. Clear? Yes or no? Yes. Good. Clear? So this is a composition of a proton and neutron. Clear to everyone? Now dear student, we are going to discuss question number 1.32, and here again we have two parts in this question. First part is given to you, consider an arbitrary electrostatic field configuration and a small test charge is placed at a null point. Okay. Dear student, do you know what is null point? Null point is a point at which we will find net electric field 0. Clear? Okay. So that the equilibrium of the test charge is necessarily unstable. It means, let's suppose if we are placing any test charge, it is highly unstable or it is in the position of unstable equilibrium. Clear? So now concentrate. Let us try to understand what is the given statement. Clear? So let's suppose actually we have to prove that if we place a charge at a null point, it is an unstable equilibrium. So how can we prove it? So let's suppose if we take here a contradiction, let's suppose we assume the charge that we are placing at a null point, that is in a stable equilibrium. It means let's suppose I am assuming, let's suppose we have any configuration we don't know. Let's suppose we have here Q1, Q2, Q3, Q4, Q5. We don't know what is the configuration, but we have a point. Let's suppose this is point P where we have net electric field 0. Clear? Let's suppose if we place a charge Q at this point. Clear? So definitely when electric field is 0, there is no net force this is acting on this charge. And we are assuming, actually we don't know, but we are assuming, let's suppose it is in stable equilibrium. Clear? So the charge in stable equilibrium. So actually what is condition for a stable equilibrium? So if we displace this charge in any direction by small amount, a restoring force will act on this charge, and this charge again try to come its original position at point P. Yes or no? Yes. It means we can see on this charge electric field will act in one direction, either this is inward direction or it is outward direction. If we have positive charge, it will act in a inward direction, and if you have negative charge, it will outward direction. Clear? Or let's suppose we can see we have charge Q. So this is, let's suppose we have a charge Q. So restoring force will act in inward direction. Clear? Now, so we can see when restoring force is acting in an inward direction from all the direction. Clear? It means we can see according to Gauss law. According to Gauss law, if we draw here a Gaussian surface, we can say there is some electric field lines that is going inside this Gaussian surface, and we can say definitely there is some electric field is to be present. Yes or no? But we know at a null point we have value of electric field 0. So actually this is a contradiction of our statement. Clear? Again I am saying to you, initially we are assumed that let's suppose charge in a stable equilibrium. If charge is in stable equilibrium, there should be, if we displace a charge by small amount, a restoring force it should act, and it should act like this, the charge again come to its original position P. Clear? When electric field is acting in the same direction, it means we can say there should be net electric field here. Yes or no? But it is given in a question, we have a null point. So it means this is a contradiction of our statement that we have assumed. Yes or no? Or we can see here definitely this statement that we are assumed that charge in a stable equilibrium, that is wrong. Clear? So we can say charge in this situation we have unstable equilibrium. Clear to everyone? Okay. Now if we talk about option number B or part number B, verify this result for simple configuration of two charge. clear, same magnitude and the same sign. So let's suppose I am taking here, let's suppose this we have charge q, and let's suppose we have charge q and this is also charge q. It may be, both charges may be positive, it may be negative. So definitely we know at midpoint we find here net electric field 0, or at midpoint on the line joining between these two charges we find null point. Yes or no? Because if we take positive charges E1 and E2, it act like this, they will cancel to each other. Yes or no? So it means this is a position of null point. Clear to everyone? Now if we displace here a charge q in a right direction, listen carefully, in a right direction, definitely we can say the charge will come again to its position P. So we can say here restoring force is acting. If we displace this charge q in left direction, restoring force is act in this direction. So again it will come to position P. So in a horizontal direction we can say this charge is in stable equilibrium. But what will happen in a perpendicular direction? Let's suppose we are taking a point P at this point. Listen carefully. So at this point P, we can see an electrostatic or electric field will act in outward direction. Here electric field is also acting in outward direction. So net electric field we will find in the vertical upward direction. Clear? It means if we displace a charge by small amount, it will go away from point P and it will never come again to point P. Clear? It means we can say in a vertical direction charge is in unstable equilibrium, but in a horizontal direction charge is in stable equilibrium. Clear? So overall if we say that in this configuration also charge is in unstable equilibrium. Yes or no? So we can say in the configuration that is related to point charges, charge is again we can say in unstable equilibrium. Clear to everyone? Now dear student, we are going to discuss question number 1.33. In this question it is given to you a particle of mass small m and charge minus q enters the region between two charge placed initially moving along x-axis, okay, with the speed Vx. The length of plate is L and a uniform electric field E is maintained between plates so that the vertical deflection of the particle at far edge of a plate is this one. Clear? So now concentrate on a screen. Let's suppose, my dear student, I am assuming here two plates. Let's suppose this is one plate and let's suppose here we have second plate. Listen carefully what I am saying to you. Let's suppose here we have positive charge and let's suppose here we have negative charge. Clear? Actually a charged particle that enters between these two plates. So I am assuming, let's suppose a minus q charge is entering from this side and this is very close to this plate. Clear? So definitely we can say electric field is actually acting in the downward direction because electric field is always from positive plate to negative plate. So we can say this is E. Yes or no? So when negative charge particle enter from this side, definitely we can see a force will act on this charged particle and it will move like this. Yes or no? Because we can see here a force will act on this charged particle in an upward direction because this is negative charge. So can we calculate here value of acceleration of this charged particle in vertical direction? Yes, we can write like this: force, this is acting in a y direction, this is QE, but QE in what direction? Upward direction. Clear? If we are not taking the direction into consideration, you will write here minus. Clear? But I am saying I already assume that force this is acting on this charged particle in vertical upward direction. Clear? So we can write like this: this is m times of AY. Clear? So from here we can say AY, this is given by QE by m. Clear? In this question it is given length of this plate is given to you, this is L. Clear? So we can see in horizontal direction this charged particle is having velocity Vx. So let's suppose from this point to this point the total time taken is t. Clear? So we can write like this because in a horizontal direction there is no external force is acting. So we can write like this: Sx equal to Ux into t. Clear? Sx is given to you, this is L, it is equal to Ux. Ux we can say this is equal to Vx and multiplied with t. Clear? So we can write like this: t, this should be given by L upon Vx. Clear? So Now we can apply here equation of motion, because in vertical direction we have a constant acceleration q, e and m, all are fixed. Clear? So we can write like this: Sy, this is given by uyt plus 1 by 2 ayt square. Clear? So initial velocity in vertical direction we have 0, so this is 0 plus 1 by 2. Acceleration in y direction, this is q e by m, and total time taken. So in a horizontal direction from this point to this point, the total time taken is same as it is going in a vertical direction. So we can say time is what? This is L upon Vx whole square. Clear? So this is our objective in this question, is to calculate deflection. So let's suppose I am assuming deflection in the vertical direction is y. Clear? So we can write like this: y, this should be equal to QE, this is L square upon, we can write like this, 2 m, and this is Vx square. Clear? So we have to prove only this deflection. So this is our proved, we can say proved expression. Clear? QEL square upon 2m Vx square. Clear to everyone? So like this you can apply concept of we can say motion in a straight line. Yes or no? Or actually this is a motion in a plane, because particle is going in an x direction as well as in y direction. Clear? So actually you can assume it's just like a motion of a projectile motion. Yes or no? And definitely if we compare this motion of a projectile in a gravitational field, in a gravitational field if you throw any particle like this, clear, and we can say here this particle actually move like this if we talk about gravitational field. But most important part, we have electrostatic force is very large compared to gravitational field, that we have already seen. Clear? So we can say in comparison to gravitational force, electrostatic force is very large. So we are actually neglecting here gravitational force effect. Yes or no? So this is all about this question. Now dear student, we are going to discuss this question 1.34. Suppose that the particle in exercise 1.33 is an electron projected with velocity Vx equal to 2 into 10 to the power 6 meter per second. If E between plates separated by 0.45 centimeter is 9.1 into 10 to the power 2 Newton per coulomb, where will electron will strike upper plate? Clear? So actually this is the same. If we replace charge q with electron, then actually we utilize same formula, this one, QEL square upon twice m Vx square. Clear? So we can write like this: y, this is given by QE L square divided by, clear to you? What is formula? QEL square divided by twice m Vx square. Clear? In this question it is given to you value of q we have, this is charge of an electron. So we, objective is what? Here our objective in this question is to calculate where will electron strike the upper plate. Okay, and E between parallel plate, that is given to you, and it is separated by this distance, it means y is also given to you. Clear? So we can say our objective in this question is to calculate L. Clear? So we can write like this: y into twice m Vx square divided by, we can say this is QE. Clear? So now if you put here value of y, this is what? 0.5 centimeter. So 0.5 into 10 to the power minus 2. Clear? Okay. We have to mass of an electron, this is 9.1 into 10 to the power minus 31 kg. Clear? Vx is given to you 2 into 10 to the power 6. So we can write 4 into 10 to the power 12. Clear? Divided by charge of an electron 1.6 into 10 to the power minus 19, and value of electric field, this is given 9.1 into 10 to the power 2. Clear? So now if you calculate this one and this one cancel out, this is minus 19 and we can say this is minus 12. Yes or no? So we can say this one and this one is cancelled out. Clear to you? So from here we can write like this: L square, this should be given by 0.5, this is 1 by 2 into 10 to the power minus 2 into we have 2 into we have 4. Clear? Divided by, this is what? 1.6. So we can write like this: this is 16 by 10 into we have 10 to the power 2. Clear? Yes or no? So from here we can say this one and this one cancelled out, 2 and 2 cancelled out. Clear? So Now we can write value of L square like this. L square, this should be equal to 4 into 10 to the power minus 2 and divided by, we can say 16 into 10. Yes or no? So now if you take square root, we can write like the 2 into 10 to the power minus 1 divided by 4 and under root of 10. Clear? So we can say this is what? 2. So from here we can say this is 1 by 20 under root of 10 meter. Clear? You can also calculate this is in centimeter. Yes or no? Yes. Clear to you? So you can also calculate in centimeter. How? So if you multiply it with 100, you can write like this 20 under root of 10 in centimeter. Clear? We can say this is 5. Now we know under root of 9 we have 3. So this is 3 point something. So we can say approximately we can write 5 by 3 centimeter. Yes or no? And approximately we can say this value we will get 1.6 centimeter. Clear to everyone? Yes or no? So this is all about this question.